All right, so today we're going to look at section 12.1. We're going to look at conic sections. Okay, and so what are conic sections? Very quickly, what we have is we have two cones, okay, a double right cone, and they're intersecting at the apex of both cones. And then we take a plane and we slice the cones in certain ways, and you will produce different shapes. A parabola is if I have a slice only on through one cone. Then you have a circle where it's horizontal. An ellipse is a diagonal all the way through the cone like that. And then the other one would be a hyperbola. And these are the ones we're going to be looking at. But there are other ones you can show how you can do a line and a point and things like that. But we're not going to worry about those. So each conic section has a geometric definition that describes a property at every point on the curve. So we're going to look at these shapes differently than what we have seen in the past. The conic sections can be graphed in a coordinate plane and can be represented by a second degree equation in two variables. Here is the generic or the general second degree equation that will generate these shapes. Okay. And so the one right here is this piece right here. So that piece, that term right there does some interesting things to the curves. And we're really not going to explore this one. I'm just going to give you the basics here. So usually this term is going to be 0. Okay, and I'll explain what this term here does in just a moment. Which is now. In this unit, we're going to examine the conic sections where this coefficient of the xy term is 0, resulting in a horizontal or vertical axis of symmetry. A non-zero xy term results in the conics with an axis of symmetry that is neither horizontal nor vertical. So in other words, it rotates it, and we're not going to worry about those types so much. If you decide to go into the science of orbits and planets and stuff like that, then you will definitely be dealing with a coefficient here that is not 0. All right. So if there is no bx term or bxy term, then it kind of turns down to these things, and you can kind of identify which kind you have based off of this little chart right here. As long as the bxy term is 0, that one does not exist. Then if a and c are both are not both equal to 0, okay, you'll have a parabola. So a or c, but not both, have to be equal to 0. So that means you have one either x squared or one y squared. If they are both different and positive, you'll have the ellipse. If they're equal, you'll have a circle. And if a and c have opposite signs, then you'll have a hyperbola. So that's kind of a quick way you can kind of tell. And then I'll show you how these equations come about and stuff. Well, today we're going to look at the parabola. So that was your basic overview of conics. We're going to focus our attention to the parabola today. Here is the parabola and the parts that we want to look at. So this is a very simple form of it. So here's the graph of y equals ax squared. It's a parabola whose vertex is at lies on the x. The vertex 0, 0 lies on the x axis of symmetry. Every parabola has a property that at any point is equal distance from the point called the focus and a line called a directrix. So this is the vertex. This is the focus. And any point on this curve is exactly the same distance to the focus and to this horizontal line or vertical line, depending on our situation, down here, which is called the directrix. Okay. The axis of symmetry is this one right here. This is where the parabola folds in half. We've talked about the axis of symmetry before. And so that's its role right here. The focus is on, and the vertex are both on the axis of symmetry. It is perpendicular to the directrix. Okay. And this is the definition of a parabola. Every point on the parabola is equal distance from the focus to the directrix, the same distance. So from that, we can then write a standard equation of a parabola with the vertex at the origin. This is the simplest one. We're going to actually move it along in later units where we're going to move the vertex to a different location other than the origin. But for now, we're going to focus on the origin to see how this stuff happens. So here's what we have. We can have with x squared, where the x is squared, this is your normal parabola that opens up or down. If y is squared, then it's going to open right or left. And so you see the axis of symmetry will be horizontal. It's going to go sideways. Okay. The focus, if it's the vertex is at 0, 0, the focus is going to be at 0p, and the directrix will be at y equals negative p. Okay, and we'll show you how to find those values here in just a moment. But that's how that works. Okay, and then for the horizontal one, it just changes location. So p is now on the x coordinate, and the directrix is going to be a vertical line, x equals negative p. So how does this look in real problem sets? So here we're going to do an example. Identify the focus and the directrix of this parabola given this equation right here. And then we want to draw the parabola. Well, you'll notice that we solved this one here, this x equals, but it's this equation right here. Okay? So if I put it back into this form, then this equation right here, multiply both sides by 4 over 3 to move it over here, I'm going to get 4/3 times x is y squared. And then why do I want to do this? Because that number that's in front of the x is that number that's in front of the x. And you'll notice that p is part of that number. So then I can take this and say, well, 4 times p is 4 over 3. And then I can just basically solve this for p. 4's drop out, and I get p is equal to 1/3. And I need that because that allows me then to find the focus and the directrix. So my focus now is going to be at the point 1/3, 0. And the directrix is going to be the equation y equals negative 1/3. Okay, and then that allows me to graph this. So we can take our equation. I'm going to extend this out here to here, and we will do that there. And what I did here is 1, 2, 3. Because we have a 1/3 here, I want to show it to you. Expand it out. 3. And then we'll go upwards the same way. Okay. So the directrix is at negative 1/3. So we'll come over here, and you want to draw your directrix as a dotted line. Although it's kind of part of the parabola, it is not on the parabola. Since it's not part of the parabola, we draw it as a dotted line. The focus is at 1/3, 0, which would be right here. This will be the focus. This is the vertex at 0, 0. Okay, so this and we'll label this in again. And then what we have is we have this axis of symmetry, this focus. So every point on the parabola is going to be the same distance from here and from here. So how does that look? We can actually make a little table and kind of plug in some numbers if you wish. You can come over here, since it's a y squared, you can plug in 1 for y, and you're going to get 3/4. Okay. You can plug in 2. That's not gonna, I can't go up to 3, so you can plug in the numbers in here, and you can get some values, and you get something that looks like probably about right here, and then another one is kind of right about here, and then you can draw this little curve. This is the parabola, and then through that one over there. So there's our parabola. This is the focus. 1/3, 0. X equals negative 1/3. This is the point 0, 0, or vertex, and that is your parabola. Okay. focus in a parabola does a lot of interesting things. Oh, I'm ahead of the game. Let's go down and do this example here. So here, we want to write the equation of the parabola that we see here with the focus at 0, -3. Okay, here is the parabola. You see it opens downward. Since it opens downward, it has to be part of this equation right here, this equation model, 4py. Okay, and because of that, we know the focus is going to be at 0p, which means if that's where the focus is, at -3, we know that p is -3. And once I have that value for p, then I can just plug it into my equation right here, and I have it. So then x squared equals 4 times -3 times y, or x squared equals a -12y. And there's my equation of that parabola. So the neat thing about parabolas is if I make them into a three-dimensional shape, is called a parabolic reflector or parabolic dish. You would have seen these things. This is your satellites, antennas, big curvature stuff, and if you go look at it, observatories that have the radio dishes and stuff like that, they look just like this. Look on everybody's houses who have direct TV. They are shaped something like this. Look at every headlight of a car, every flashlight. The reflective image is this thing right here. And the focus plays the role of where the light bulb would be or where the receiver is. Okay, if you watch football, you'll see these dishes out on the football field because it'll have a microphone sitting right here, and it is used to capture sound from the field. Okay, so this is how you can do this. But because of this, the focus is equal distance from every point on here. Anytime something comes in, it will bounce off the parabola and go right to the focus. And likewise, if I put a light bulb and it shines a light bulb in all directions, it will hit every point on the parabola and bounce straight outward. And that's why you get a flashlight beam of light. Okay? And so this is the practical use for this. So here's an example. You have a microphone, has a parabolic reflector around it to capture sound. The microphone is placed at the focus of the parabola to reflect as much sound as possible to the microphone. Write an equation for the cross-section of the reflector. And how high is the microphone above the vertex? So in other words, where is the focus? Okay. So this point is on the curve. And here's my parabola, goes through 0, 0. So again, since it opens upward, we know it is of this form right here. And we know that that point is on the parabola. So this is an x and a y value. So we can solve for p. Since x is 10, so this becomes 10 squared. 4 times p times 5. So 100 is 20p. So p is equal to 5. So what does this mean? This equation right here is x squared equals 20 times y. So there's the equation of this cross section. And where is the microphone going to be? It's going to be at the point 0, 5, right there. 0, 5 is your focus. So put the microphone there, and you're going to get all the sound reflected that's captured from this dish. Okay? So that is how parabolas are looked at. And the directrix, by the way, if that's where the focus is, the directrix is down here at -5. So this is y equals -5, right down there. Because this is equal distance from the focus to the directrix, so is the vertex. So if this is at 5, then the directrix is directly below it at -5. It has to be exactly the same distance apart. So that's how I know it was down there at -5 very quickly. Okay? So that's parabolas, and we'll take some more problems and questions together in class.